All right, everybody. So this section is all about transformations. How to create new functions from old functions. We're going to be working with transformations, shifting, vertical, horizontal shifting, stretching, compressing, reflecting, all of those fun things. You learned all of these in Algebra 2. Okay? Me and Mrs. Apples, we taught you all of these transformations. I know I did. Shake your head. We definitely did. What we did was we took it chapter by chapter. Like we studied linear functions, we taught you linear transformations. We studied quadratic functions, we did quadratic transformations. We did exponential functions, we did exponential transformations. Okay? And then we did it, chapter by chapter. What we're going to look at today is generalizing. Doesn't matter what functions we're working with, how do we know what transformations are happening based on a general transformation rule? Okay, and then at the end of this section, we talk about combination functions and composition of functions, like f of g of x and g of f of x and things like that. Okay, so that's this section in a nutshell. In my opinion, this homework, it's not too bad. Just watch out the 32 to 42 even and the 52, 53. Don't save like the last numbers until like the period before this is going to be due, because those have like the A, B, C, D, E, F, in there. So the bulk of the time was spent 32 to 42. Even. Okay. All right. So let's take a look here. Transformations. Understand that transformations are just taking a parent function, or taking really any function, but mainly taking parent functions and applying a transformation rule to them. Okay, the transformation rule can be, shifting, stretching, compressing, reflecting, doesn't matter. Okay, they will all apply the same way to each function. We'll input it into that function, and then the types of functions will tell us what we have to do with it. So let's talk about each one of them. What we see down here are the shifts, okay? Remember that if you take the f of x plus c, if the plus or minus c is sitting on the outside, that is moving it up or down, okay? Like x squared plus 2, where it's just x squared plus 2, not x plus 2 squared, but x squared plus 2. That's an up 2 for the quadratic. X squared minus 2 would just be shift down 2 for the quadratic, okay? If I change what's inside the parentheses, or I change the input value, that's changing the x value, that's moving something horizontally left or right. And then this is addition and subtraction here. The catch to that is horizontal is always weird in that if you have like an x minus 4 on the inside of the parentheses, that's actually going to move to the right 4. X plus 4 inside the parentheses will actually move to the left 4. Okay? So this is just a diagram showing you just a generic function and then how it translates. Yeah, that's just a generic weird function and how it translates. So this is y is equal to f of x. This is just the shifts, right? We'll talk about stretches and compressions in a second. Here's y is equal to f of x. I can move it up to f of x plus c. I can move it down to f of x minus c. I can move it right to x minus c in parentheses. I can move it left to x plus c in parentheses. Okay? Inside parentheses means something horizontal. Outside parentheses means something vertical. If I'm adding or subtracting, that's what denotes a shift. Addition and subtraction. So, what would be a stretch and compress? Well, now you might see it called here. I always call it a compression because that's just what we use, the terminology that we use in Algebra 2. They like to use the term shrink. Okay, they call it like a horizontal shrink. I'll call it a compression. So if you ever see a shrink, yeah, it's compression. I don't know. That's okay, so let's consider the stretching and reflecting. Okay, stretching and compressing deals with multiplying the function by a factor. Okay, multiplying it by like a scale factor. Okay, multiplying it by a constant, a value. For the verticals, okay, that's when I multiply it on the outside. The constant must go on the outside. It must happen to the entire f of x. Okay? That's when a number is being multiplied to the outside. If that number being multiplied to the outside is a whole number, meaning a number greater than 1, then I know that it's going to be a stretch, a vertical stretch. If that number is less than 1, so greater than 0, okay, if it's like 1 over c, okay, 1/2, 1/3, 1/4, that's when it's what they would call a shrink, a compression, okay? If you put that on the inside, it turns from vertical to horizontal. And again, weird things happen with horizontal. If it's a horizontal compression or shrink, if it's a horizontal compression, it's going to look like a whole number on the inside. So if I take like f of 3x, that's actually a horizontal compression by 1/3. Okay? If I take a fraction on the inside, that's a horizontal stretch. Okay? So if it's like f of 1/3 x, that's a horizontal stretch by 3. Weird things happen with the horizontal stuff. And then the reflections, if I take negative f of x, that's a reflection across the x-axis. If I take f of negative x, that's a reflection across the y-axis. Remember, think about input versus output change. If I change the output value, meaning I change the y value, I change the f of x value, that means I'm changing the verticality of it, right? I'm changing the verticalness of it. That means I'm changing across the x-axis, the horizontal axis. If I change the input value, if I change the x value, I'm talking about reflections here. If I change the x value, that's going to change the horizontalness of it, right? So that means it's going to be a reflection over the y-axis. I know I'm making up words now. That's going to be a reflection over the y-axis, okay? Showing you here, just a generic, here's that y is equal to f of x thing again. It's that weird curve. If I take a vertical stretch, remember vertical stretch is taking those points and multiplying by the y values, right? I'm multiplying by the output values, multiplying a certain number by the output value. So that means I'm going to increase the size of it in terms of the y. The x is going to stay the same, but the y value is going to stretch out or shrink down, right? There's the 1 over c. That's like a 1/2 f of x, right? Just going to decrease all my y values by a factor of 1/2, right? Multiplying with the y values by 1/2. If I were to pull it this way, right? If I were to horizontally stretch it out, that would be that f of 1 over c x, or f of x over c, how they put it here. Okay? That would be a fraction on the inside. If I'm horizontally compressing it, that would be like a f of c times x. Okay? Notice the reflections down here. If I reflect it across the x-axis, I'm changing the y value, I'm changing the verticality of it. If I reflect across the y-axis, that's when I'm changing the input value, the negative x on the inside. Okay? Special point to bring up here. If I talk about the, what point is that? X comma 0? What's that called? X-intercept, right? That's called the x-intercept. Does a vertical stretch or compression change the x-intercept? Does a vertical stretch or compression change the x-intercept? No, it does not, okay? This will never get changed by a vertical stretch or compression because I am only going to be multiplying by the y value. And since it's 0 times that compression or stretch, it's not going to change. So think about the y-intercept then. Does a horizontal stretch or compression change this one? No. Okay. The y-intercept will never get changed by a horizontal stretch or compression. Just like the x-intercept will never get changed by the vertical stretch or compression. If it runs through 0, 0, will that point ever get changed by a stretch or compression? No. Okay. All right. Let's consider, yeah, Caleb.
For the horizontal stretch, if it's c over x, would that
X over c.
I know, but if it would be c over x, would that be a stretch?
Then it would turn the function weird. Like then it would be like a 1 over x would be like a hyperbola. Yeah, that's not technically a transformation. Okay, let's consider the trigonometric equations. Yeah, because those are the weirdest type. Remember, like phase shift, amplitude change, period change, and all that fun stuff. Yeah, that's what we're not going to go too in depth right now, but think about how these transformations relate to that. This figure illustrates the stretching transformations when applied to the cosine function. If I take a number on the outside of a trigonometric, especially sine and cosine, then it will increase or decrease the verticality of it, right? If I put a 2 on the outside, it's going to be a vertical stretch. It's going to take all of those, it's going to basically take the amplitude and increase it, right? Bigger, it's going to make it bigger if I put a 2 on the outside. If I shrink that down, look at me, I'm using the word shrink now. If I compress that down toward the x-axis, that's like putting a 1/2 in front of it. If I change that to the inside, that means it's going to stretch or compress horizontally now, right? So it's going to change. Notice how the x-intercepts weren't changing, right? Now if I do this, that's going to change those x-intercepts. The y-intercepts were changing here. The y-intercept does not change here when I do the horizontal stuff. And now I'm only talking about stretching and compressing. Shifting, obviously, it will change the intercepts. But just for stretching and compressing, it will not change, or it will change sometimes, but not always. So cosine of 1/2 x, that would be like a horizontal stretch by 2, right? Horizontal stretch by 2, meaning that's going to change the period of the trigonometric function. Cosine 2x, that's a horizontal compression by 1/2, okay? So like if here is cosine x, right? Cosine 2x is going to compress it in toward the y-axis. It's going to make the curve happen faster. If I pull it, it's going to make the curve happen slower, right? That cosine 1/2 x, horizontal stretch. All right, so let's take a look here. We're going to start with the parent square root function. Y is equal to square root of x. And what we're going to do is use that to transform into y equals square root of x minus 2, y equals square root of x minus 2, y equals negative x, square root of x, 2 square root of x, and y is equal to square root of negative x. Okay. So let's start off by graphing my parent. Okay, I'll graph my parents in blue. Remember that this is just a positive root, right? Just a positive root. So like 0, 0, 1, 1, 4, 2, 9, 3, right? Okay, I'm going to underline it for every color that I use. Just the top half, not the bottom half. If I wanted the bottom half, I would have to I'd be forced to put a plus or minus here, which we'll talk about here once we do that one. All right, so let's start going down the colors. What's that going to do? What's that going to do? What transformation is happening there? What's a minus 2 on the outside going to do? Down 2. Left and right is inside. Up and down is outside. So it's going to go down 2. It's going to take all these points and shift it down 2. Here, 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 here. That's that one. Okay. So what about that one? What does that do? That's the right 2. That's to the right 2. I know it's almost counterintuitive. You're thinking, oh, it's a negative 2. It must move to the left 2. No, it's horizontal. It's weird. It goes to the right 2. Here, 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 and would be at 11 over there. Okay, let's take a look here. Again, we're always going back to the blue function, back to the parent. We're not compounding these, we're just going back to the parent. Okay, negative on the outside. What kind of reflection is that? Reflection over what? The x-axis, right? I'm changing the verticality of it. changing the y value of it. I'm not changing the input value, I'm changing the output value. So therefore, it's going to be a reflection across the x-axis. It's basically just going to flip the blue one downward. It's going to give me the other half of the sideways parabola. Let's put it, is yellow okay? Yeah, we can see yellow. Okay, what is that doing? 2 radical x. Vertical stretch by a factor of 2, right? Vertical stretch by a factor of 2. Does that change my first point? No. That first point stays where it is. The second point, 1, 1, turns into 1, 2. 4, 2 turns into 4, 4. Multiplying each y value by 2. 9, 3 turns into 9, 6. What's this transformation here? This last one here. Well, I'll put this, I'll do a dotted line. There we go. What's that last one? Reflection over the y-axis. Yeah. So just going to do here, and then 4, -4, +2, -9, +3. Questions about that? I would suggest there's a couple of homework problems where you have to do that, where you have to transform. Either make a separate graph every time or try to use different colors. It's kind of weird. Okay. All right, we're good here? Any questions there? Perfect. Let's take a look here. Move this over here, make it a little bit bigger. Oh, I guess not. All right. Sketch the graph of the function f of x is equal to x squared plus 6x plus 10. And I'm going to ask us if we could, let's not put it in our calculators, and let's not find the zeros. Let's try to figure out what transformations happen to it. The problem with this is that it's in standard form. Does anybody remember what type of form I should put it in to see the transformations? Not so good enough. Not Poisson. This is quadratic. We're talking about linear. Standard form versus vertex form. We've got to put this into vertex form. Okay? Vertex form will show the transformation because vertex form shows the vertex, shows where it went from 0, 0 to wherever the vertex is. It will move 0, 0, the vertex 0, 0 around the graph. Okay, well, this is a bear. This is going to be fun. We have got to take f of x is equal to x squared plus 6x plus 10 and turn it into vertex form. Does anybody remember how we do that? I taught this to you guys. Well, you understand. I'm going to say I, but I'm just saying we. Anybody remember how to do that? It's our good friend completing the square. Okay, what we have to do here is complete the square with the first 2 terms. Okay, so we partition off the first 2 terms, leave the 10 sitting in the outside of parentheses. What completes the square? What do I add on the inside to complete the square of x squared plus 6x? Half of b squared. Half of 6 is 3 squared is 9. So we add 9 to the inside. Now, if I add 9 to the inside, what do I have to do to the outside? Subtract it. Remember, balance the equation. If I add 9, my f of x is stuck, right? I would have to add 9 to f of x, and I don't want to do that. If I have to add 9 inside, I have to subtract 9 to keep the equation balanced. Okay? These must always be opposites when you're completing the square like this. So that means we've got f of x is equal to, this gets us an x plus 3 squared plus 1. So what are my transformations? I've got two transformations happening here.
Up one and to the left.
Very good. Up one, left three. Up one, left three. Up one, left three. And there's my vertex. And if I'm sketching, you treat this like that's your new origin point. One, because I'm not stretching it or compressing it at all, right? There would be an A value sitting out front if I were to stretch or compress it, and I'm not. So it's like over one, over two, up four, over three, up nine. Which makes sense. Where's our y-intercept? 10. Left one, up one, left two, up four, left three, up nine. Here's my problem. Pretty precise sketch. Okay? But the best route to take here, if you truly want to see the transformations, is to put it into vertex form by completing the square. All right, let's take a look at some trig ones. I'm actually going to get these out of here because, I'm going up to 10, and my graph's going to look a little different because I just want to go to -1, +1. Sketch the graphs of the following functions. Okay, so the first thing that I have to do is figure out my parent. Where's mine? This is one of the only ones that we don't do in algebra 2, so I always got to make sure I'm doing this right with you guys. Yeah. Okay. So I am going to create myself kind of a wide axis here. All right. I'm going to write the parent in, which is sine x. Okay, so starting at 0, 0, and then it will continue, right? Okay. So that we're going to call sine x. Remember, this is pi, and this is 2 pi, where it crosses again. This is negative pi, and this is negative 2 pi. Okay, so what's going to happen, and I guess I should, if I'm going to write that in, I should write +1 to -1. So what's going to happen with this transformation?
Compression by 1/2.
Compression by which type? Vertical or horizontal compression by 1/2? Horizontal compression by 1/2. It's going to take all of my x values and multiply them by 1/2. It's going to keep the y values the same, but multiply all x values by 1/2. So this pi now becomes pi over 2, right? This 2 pi now comes where? Pi. 0, 0. Does 0, 0 change? Nope. So it's going to go like this. Okay. There we go. That should have went up to 1, but you get the picture. Okay. Again, I should have gone below. Yeah. But you get the idea. Horizontally compressing it toward the y-axis. Okay. And I'll make special note of this, so it's written in there. This is a horizontal compression by 1/2. All right, let's talk about the next one here. I see two things happening here. I'm going to again make myself a -1, pi, 2 pi, negative pi, negative 2 pi. Okay, this is my parent again. I see sine x. Well, that's not right. Whoops. Oh gosh. Yeah, okay. I'm out of practice doing this. All right, 1 minus sine x. What are the two things that are happening? Yes, there are two things. Caleb?
Horizontal reflection.
Horizontal reflection. Reflection, what do you mean by that? Reflection over the x-axis. Good. Yeah, reflection over the x-axis. And, because that's the negative, right? That's the negative. And what else? Up one. Up one. Up one. Excuse me. Okay. Now, I always like to, let's do this in our calculator real quick. Because it's interesting to point out, what do we do first? Do we do up one, then reflect? Or do we do reflect, then up one? Uh-oh. Bearded wonder, everybody. No. I do. Yeah. Yeah. Go pick up sheets. What a nice time. But I forgot I got me. Okay, sorry. And we're back. 1 minus sine x. Okay, let's see what happens here. Oh, that's not right. That's still on a scatter plot. Hold on a sec. There we go. I'm going to zoom 6. Good. And you know what I'm going to do? I always like to change my window around and work with trig ratios. So I've got window. Let's make it a y min at -1 and a y max to +1. Oh, and I shouldn't have done that. Why shouldn't I have done that? Because I got up, of course. Okay, I'll go y max to 2. There we go. Okay, so just shifting it up 1. Do you see how it shifted up 1 here? I'm just going to use this graph. Okay. Do you see how it shifted up 1? Yeah? Now, take a look here. If I had just shifted up 1, then I would start by going, right? Okay, if I just shifted up 1. So this is shifting up 1 and then reflecting, okay? Then reflecting. So now, actually I did the reflection first, didn't I? If I just do this, I'm looking here, sorry. Negative sine x. Yeah, it did the reflection first. And then it shifted it up 1. Okay? This is just negative sine x. This bottom one is negative sine x. This going up 1, that second one, the top one, that's the up 1. So it did the reflection first and then it shifted it up 1. Okay? Reflection first and then shifted it up 1. Let me put that on the screen to get this to go away. Oh, review. Get out of it. Get out of it. Okay, this is negative sine x, and this is 1 minus sine x. Okay, just showing that this is just a reflection, and then I shift it up 1 after the reflection. Okay. All right. Okay, so let's talk about this example. This is a really funky one. I had to do this one like 3 times. Okay. What time is it? We got plenty of time here. Yeah, plenty. Okay, figure 9 shows graphs of the number of hours of daylight as functions of the time of the year for several latitudes. Given that Philadelphia is located at approximately 40 degrees north latitude, find a function that models the length of the daylight at Philadelphia. What? Now, think about this logically. Length of daylight throughout the year. What happens in the summertime? Day gets longer. What happens in the wintertime? Day gets shorter. And then it expands and contracts and expands. It goes throughout that cycle the entire year, and that continues from year to year. So it is cyclic. It goes up and it goes down, and it goes up and it goes down, and it goes up and it goes down. Okay? That's demonstrating sine or cosine, whatever we have here. Let's say this. Let's say it's sine. Okay. Why do I say it's sine? Well, because that it's going up right off the bat. Right? It's going up right off the bat. We can use this as kind of like almost like our origin point. Okay. So we just have to figure out what types of transformations we have going on. Okay. So the first thing that we've got to do is figure out the how much it shifted to the right. Okay, how much it shifted to the right. Well, where does this start? You know, I'm looking at the book solution and it said, well, it starts right about there, right about in the middle of March. So they estimate it to be the 80th day of the year, the 80th day of the year. So we are going to say that this got shifted. If we assume 00 is a January, this got shifted to the right 80 days. Okay. How much did this get shifted up? 12. So this is an up 12. So we know right off the bat, if we're working with a sine function, we know that this is going to be on the inside, x minus 80, and then a plus 12 sitting on the outside. Now, is this just a normal sine curve? No, it's not just any normal sine curve. So we just have now we have to figure out how much we horizontally stretch a compression or how much we vertically stretch a compression. Okay, this 80 is a total estimation. How do we know that? Well, it's the 80th day of the year, I guess. That's what they're saying. That's what the book says. Okay, so let's figure out where Philadelphia is. 40 degrees north latitude. I'm looking at this line in here. Okay, now we have to figure out, let's do the amplitude now. The amplitude is always 1/2 the difference, top to bottom. That's the amplitude, 1/2 the difference, top to bottom. So let's estimate the top, and let's estimate the bottom. Okay. Basically the average of the verticality of it. Let's estimate the top to be 14.8. And let's estimate the bottom to be around 9.2. I'm taking the book's numbers so that we can reference that back if we need to. Again, this is all estimation here. So let's take the average of the difference here. 1/2, 14.8 minus 9.2. That gets us 2.8. That is the vertical stretch of it. So where does that go? Does that go inside or outside? Outside. Okay, that would be the change in amplitude. Now we have to figure out how much it horizontally stretched. Okay. Well, to do that, we take 2 pi divided by how much it actually stretched by, what the period length is. So what is the period length here? Well, we're going from year to year. How many days? 365. So it's 2 pi divided by 365. That's the horizontal stretch of it. Where does horizontal stretch go? Inside multiply. And I did not leave room for it. So I'm going to say this. The function is 2.8 sine 2 pi over 365 x minus 80 plus 12. Ooh, funky, right? That's a weird problem. Oh, I'm sorry, I cut off the 12 here. It's over there. Why are we doing this, right? Why are we doing this? We're doing this because I want to show you that you can model things like day length by using a sine function. You can actually do that. Okay? It does anything cyclic might model a sine cosine function. Okay? Good question. You know, probably not. But they presented it in the book, so I'm like, yeah, sure. Let's do it. Yeah. Yeah, I don't think so. No. if I give you a sine or cosine one, it's probably going to be more like, you know, simple, not non-word problem type thing. Yeah. Okay. Another transformation can happen when we work with absolute values. Yeah, we may not think of absolute value like a transformation, but it really is transforming the original function. What does an absolute value do? Well, it turns negatives to positives, right? Always keeps it positive. Now, what does that mean graphically? That means that it takes anything underneath the x-axis and flips it over. Okay? It takes all the y values that would have come out negative and turns it positive. So if I'm looking at this here, and that's assuming that there is no vertical shift to it. There's no plus or minus signs on the outside. If there is, then weird things happen. But if we just have an absolute value of a function, the absolute value of f of x, what it does is it takes anything below the x-axis and flips it upward. So let's first off graph x squared minus 1. Okay? Let's first off graph x squared minus 1. What does x squared minus 1 look like? What does that look like? Parabola done what? Not right. Down 1. Remember, right would be inside. Parentheses. Right, down 1. Right, so this, again, just a sketch. That would be just x squared minus 1. So now what an absolute value is going to do, it's not going to flip the whole thing around. It's only going to take the piece that's below the x-axis and flip it upward. So it's going to look like this. You know, here. Like that. Isn't that kind of cool? Yes, your calculators will do absolute value. Okay. It's in math. I think number, yeah, abs. X squared minus 1. Oop, zoom 6. You see that? So if you ever were testing it out, yes, it will do absolute value. It will do absolute value. So again, what did we really do there? It took this piece here and turned it positive, flipped it, flipped only that piece positive. And again, that's assuming you just have y is equal to absolute value of f of x. When you start putting other, that's a vertical line. When you start putting other transformations on it, like a shift up or down, that's when it's a little bit more complex. About 10 minutes left. Let's talk about them and then we'll we'll finish up tomorrow. That's a lot of material. That's a lot of words on a page right there.